Okay, so the main point that you discussed in the lectures last week was the semantics for first order logic. So semantics for first order logic. And I will just briefly go over the main points. So the first thing to note is that for propositional calculus, in order to define semantics, all that we needed was a truth assignment to the variables. Now we have a much more complicated system. So in order to define semantics, we start with a language. So we are given a language. Language for first order logic, I mean that we have some function relation symbols R1 to Rk, and we have some function symbols, and we have some constant symbols. So this is the way the language looks. We have relation symbols, function symbols, and constant symbols. And now we want to define semantics for the set of first order formulas over this language. So the semantics depends on two components. So in order, what is a semantics? A semantics for the language, first order language, logic over L is a rule that assigns T or F to every well-formed formula. So in order to have such a rule, what we need is the components that we need. So we need to fix, first of all, a structure for L. So a structure for L is a universe and an interpretation for each of the symbols of the language. So a structure for L is the universe and interpretation for the symbols. So this is a universe set. And interpretations for the symbols of L. So that's the first component that we need. And what is the second component that I need in order to assign true or false to every well-formed formula? So let us look at an example. So look at the simplest example. So say L, my language has, so my vocabulary has some one relation R and two functions f and g, two place functions, and two constants a and b. And now I define a structure for this language, which is going to be my universe is going to be the natural numbers. So that's my universe. R is going to be interpreted as less or equal than. F is going to be plus. G is going to be times. A is going to be 0. And B is going to be 1. So this is one potential, let's call it M1. It's one potential universe for this language, because it consists of a universe set and an interpretation for every symbol that I have in my language. Right, and now we can ask questions. Already we can evaluate intuitively the truth formulas of the truth value of certain formulas, but not all of them. So for example, if I have the formula that says for every x there exists a y such that x, it's not the case that x equals y, and r y x. So this is my formula phi. And now I want to know, does this formula gets the value true or false in this structure? So what does this formula intuitively say? It says for every x, I have a y which is different than x and is smaller than x. So is this true or false in this structure? It's false. Why is it false? Because we have one x that will not satisfy it, and this is the x which is 0. Okay? So some formulas we can, once we have a structure, we can already tell whether this formula is true or false. But there are other formulas that having a structure will not suffice to tell whether they are true or false. So can you give me an example of such a formula? Say my formula. So here, this will have a truth value f in M. Or in other words, M does not satisfy my phi, or M1, we call it. Right? Yes?
I'll think of an example for one.
Yeah.
O of xy.
Right. So if I take the formula psi, which is R of xy, an atomic formula, then I cannot tell whether it is true or false in this structure, because I cannot determine its value as long as I don't know what is x and what is y. So in order to determine, to have a semantics, I need the first component is a structure, and the second component then I need, so the second component that we need is an assignment of variables to elements of the structure's universe. So if I take now the assignment S that maps x to 7 and y to 9, then under this assignment M1, under the assignment S, will satisfy my formula psi. And if I take another assignment S prime that will take x to 10 and y to 1, then the same M1 under the assignment S prime will not satisfy the same psi. So this is all stuff that you have covered, right? Right. An assignment, in principle, should give me a value as an element of the structure for every variable. But there are maybe infinitely many variables, and I want to write assignment like this. So there is a very obvious claim here. So there is a very obvious lemma that say that let phi be a well-formed formula in some language L. So I use the term language for the list of symbols that I have in my logic. For language L. And M, a structure for L. And by saying a structure for L means that it has an interpretation for every symbol that I have in the language here. Then, for every for every assignment S1, S2 to the universe of M, if for every variable that occurs free in phi, for every variable, let's call it variable x, S1 of x equals S2 of x. So the two assignments agree on the free variables of my formula. Then M satisfies under S1 the formula phi if and only if M satisfies under S2 the formula phi. So things, yeah, I mean, as you can see, the first order logic is much more technical than what we saw in propositional logic, but still we can look at it, I mean, you can get the intuition of this, and the intuition here is obvious. I mean, so what, for example, what are the free variables of this psi? X and Y. So what does this statement say? That if I have two assignments, they agree on X and Y, then I can tell whether my formula is satisfied under one of them by checking another one. It doesn't matter. And that's why here, when I want to check if this is true or false, all I needed is an assignment for X and Y. So that was kind of the justification for the fact that when I gave you assignments here, all I bothered with is how the assignments behaves on X and on Y and not on other variables. Because if I have a formula and two assignments agree on the free variables of the formula, then the truth value under both assignments will be the same. And in a way, we can also look at this formula. What are the free variables of this formula? So do you remember what are free variables? I mean, there's the intuition, there is a definition. The intuition says free variables are variables that are not quantified. Remember, and the formal definition was a variable is free. If we start with an atomic formula, then here X and Y are free. Then I add another atomic formula. Again, the set of free variables is X and Y. But then I have a quantifier here which says Y is no longer free. And then I have a quantifier here that says X is no longer free. So I am left with no free variables. If we read this for no free variables, what does it tell me? What does this lemma tells me if the formula has no free variables? Yes?
It's true for any assignment?
It is, yeah, if it's true for one assignment, it is true for all assignments. For any two assignments, because any two assignments vacuously agree on the free variables of my sentence. So I don't care about how the assignments behave because I don't have free variables. And that's why we could talk about M satisfying this formula or not satisfying this formula without bothering with assignments. Because if I don't have any free variables, then I don't need an assignment. So let's just write down this corollary. So corollary, if phi is a sentence, namely it has no free variables, then for any S1, S2, M satisfies under S1 this formula if and only if M satisfies under S2 the formula. And therefore, when we discuss truth values of sentences, we do not specify any assignment. And this is a corollary because it is just the same lemma for the case that I don't have any free variables. Any two assignments agree on the empty set. So what do we need to do now? What is missing now? What do we usually do when I give you a lemma? We prove it, right? I mean, I know that we don't want to do it. But the proof here, just to demonstrate, I mean, the proof here is quite simple, and it is just by induction on the structure of the formula phi. So let me just outline the proof. So this is kind of a cleaning lemma that tells us here is why when you talk about sentences we don't have to mention assignments. Here is why when I want to mention assignments it suffices to have assignment for the variables that I see here free. So it's kind of allows us to do things the way we expect them. And the proof is by induction, by generalized induction on the structure of phi, of the formula that I want to show it. So we fix the structure, and we want to show, we fix phi, we fix the structure, we want to do induction on phi. So what is the basic? It is kind of just repeating the definition of the semantic. What is the basic, what is the atomic step in defining a formula? What? Variables and constants are not formulas. So what are the, what?
Atomic formulas.
Atomic formulas. So we have to start with the base step is atomic formulas. So let us recall what is an atomic formula. Atomic formula is just a Boolean combination of formulas of the form are a relation applied to variables or equality applied to variables. So atomic formulas are Boolean combinations. Atomic formulas are not Boolean combinations. Atomic formulas are just formulas of the type phi is either some T1 equals T2 or phi equals some R of X, Y, Z, depending on how many places are in the relation R. So atomic formulas are just applying a relation to variables and maybe constants. So let's put A here of this form. These are the atomic formulas. Now, in order to handle this, we need to do induction on terms. So we just have to say that, so just note, I will not bother to prove it, that for every term T, if S1, S2 agree on the variables in T, then S1 of T equals S2 of T. So we have to just remember, what does it mean? The assignment, I mean, I'm assuming that it's something that you have seen last time, but let me just remind you. So the assignment S, it just goes from, it's a function that takes the variables and map them to members of the universe of the structure. It takes, so it can say X is going to be the number 3. Y is going to need to be the number 5, and so on. It takes variables and maps them to the universe of the structure. Then we extend it to S prime, S hat, and S hat looks at a bigger set, the set of all terms. So here I can have things like f of x, y. And if f is plus, then it will map f of x, y to the number 8. So the terms are what I get by applying functions to my variables and constants. The constants already got a value by defining the structure. So S hat gives me a value for every term. So if I have here a term t, S hat will map t to some element of the universe. So what I'm saying is that if I have two assignments that agree on the variables that appear in t, then they will map t to the same element. If I have two assignments, if my t is x plus y, and my two assignments agree on x and agree on y, they will also agree on what is x plus y. So now we have an atomic formula. It's either of this form or of the form a relation applies to terms. And now it is, what is the definition of the truth of the formula? The formula holds. So yeah, it is a bit of a problem that I don't know exactly what you did last time. I should have looked at the video, but I don't think the video is there already. So we have here kind of two worlds, right? One is the world of formulas. One is the world of well-formed formulas. and the other one is the world of the interpretation in my structure. So I can have a formula that says, I have here x, the interpretation in the structure is S of x. So S of x is a member of the universe. It's the member of the universe of the structure. And if I have here an element which is a term, t, say x plus y, then I have t goes to S hat of t, which is an element of the structure. And now if I have here a formula that says R of T1, T2, then I look at what is S hat of T1, it's some element here, and I look at what is S hat of T2. Now I have two elements here in my structure, and I also look at the interpretation of R in this structure. And I ask, does the interpretation of R in this structure hold for those two elements? So R could be just a symbol R. The interpretation in the structure could be less than. Here I have two terms, and here I check whether the interpretation of one term is less than the interpretation of the other term. Okay? So since we have this claim that if two assignments agree on the free variables of t, then the two assignments will send this term to the same element in the structure. Then we can conclude the base step, the base step here. So we can conclude that, so the model under S1 satisfies R of T1, T2, if and only if the interpretation, so did you have a notation for the interpretation of relation R? No. What? R of M, something like that? The interpretation of R in the structure M? You did not use this notation?
I think we just reused S bar. Yeah.
But there is no. No, but I want to say R becomes less or equal. You see what I'm saying?
Yeah, I think it has a key.
We did S hat or bar.
S hat is the, S hat is the way to map terms.
Okay, so we didn't have anything.
Okay.
Yeah, we just had R. We didn't use any like RM or anything.
Okay, so, but this is, so, I have in the language, I have R, and I can give it an interpretation, and I'll call this interpretation R interpreted in M. In my structure, R is less than. In another structure, R could be equal, or greater than, or whatever. X is y squared. So I have an interpretation of this symbol in my structure. So the structure satisfies R of T1, T2 if and only if this, the pair S of T1, S of T2 belongs to R in the structure. So did you use this notation or if and only if R in the structure when applied to S of T1, S of T2 equals true? That's the type of notation that you use?
I'm pretty sure we used S hat of R of T1, T2.
Right, but I want to tell you what is S hat of R of T1, T2. I want to tell you when, you see, the notation S hat of R T1, T2, this means the truth value of R under this. Now I want to define it. So this is defined as the same thing as the question of whether, when I look at these two elements, S1 and S2, S1 of T1 and S1 F of T2, do they satisfy the interpretation of the relation? So, yeah, I'm sorry about this kind of unsmooth stitch. So how did you define this for atomic formulas? When is this true?
T1 and T2 are in the specified modes, so they give us a set of T1 and T2 that satisfy this R.
Right, so you have the set of pairs that satisfy this R. So this is the interpretation of R.
We just didn't use that symbol.
You just didn't use this notation. Okay. So my conclusion is that I cannot allow myself to torture you with notations in the exam, right? You'll be very sad about it. So anyway, what do we have here? We have a structure and we have a language. And it's very similar to our distinction between syntax and semantics. So on the syntactic side, we have terms and variables and formulas. On the semantic side, we have terms become elements of the structure, and the relation symbol becomes a relation in the structure, which means a set of pairs. Or for every pair, it is either true or false. So now, if I want to know if these atomic formulas hold in the structure, or if this atomic formula holds in the structure, all I need to know is if the relation in the structure applies to these two elements. Now, these two elements are going to be the same under S1 and under S2. Because if S1 and S2 agree on the variables of T, then they send T to the same element in the structure. So this answers the atomic formula step. And then we have to do the induction hypothesis and the induction step. And the induction step talks about how to generate complex formulas from simple formulas. So the induction step has to apply to the operations that we have for building formulas. So we have to talk about phi being phi 1 arrow phi 2, or phi 1 and phi 2, or not phi 1, and so on. And we have to talk about one more case, that phi is for every x phi prime. These are the operations that are used to generate formulas from atomic formulas. Okay, so for this, it just follows from truth tables. Since under S1 and under S2, each of those got the same truth assignment, then when I combine them in a truth table, I will get the same truth assignment. For this guy, what are the free variables of this formula? How do the free variables of this formula relate to the free variables of phi prime? Yes?
All the free variables not including x.
Right, all the free variables not including x. So now I assume that S1 and S2 agree on all the free variables here not including x. But the truth value of this does not depend on the assignment for x, because I have to check it on every possible assignment for x. So the fact that S1 and S2 agree on the free variables of phi minus without x doesn't bother me, because to check the truth of this, I don't care about what assignment is going to x, because to check the truth for all x, I have to check all possible assignments for x. So that's the induction step here. By the induction assumption, S and S1 and S2 agree on all the free variables of phi prime except for x, but I don't care about it because to determine whether it is true or false, all I care about is how the other free variables behave. So this is just the outline of this proof, and it is not much more than just a reminder of how we defined semantics. Okay, so with this I want to leave the formalism a little bit and do something which is, because I feel that I kind of, the formalism is a necessary bad, but it's not fun. We want to make sure that we can define everything precisely and that we are completely clean in terms of not becoming ambiguous. But it's not the essence of the logic. So the essence of the logic is what can be expressed with it. So let me move forward and talk a little bit about semantic notions. So we are following the same path that we followed in the propositional logic. We defined the semantics, and now we want to define semantic notions. So the first semantic notion that we want to define is the notion that is analogous to tautology. So we say that phi, so the first notion, phi is a logical truth if for every structure for the language of phi and every assignment S to that structure M under this assignment satisfies phi. So this is what was the analogous term for propositional logic? How did we call such a formula in propositional logic? A formula that is always true, no matter how we tautology. And in some places you will see the term tautology applied to first order formulas as well. I use logical truth instead of tautology to distinguish propositional logic from first order logic. But it's basically the same thing as a tautology. It's something which is always true. So let me give you examples of some tautology and examples of some things which are not tautologies. So here are some examples of logical truth. So for example, I can take, so let my phi be for every x q of x, where q is a one-term relation symbol. And I say that this arrows q of y. So this is my formula. This is my formula for every x q of x arrows q of y. Where q is a one-place relation symbol. Or predicate. So how do we show that this is always true? we have to resort to the definition of the semantics. So we know that this formula is, its main connective is arrow. So what is the only case in which it could be false? If this is true, not Q of X. If this gets true and this gets false, this will be the only case where this will fail. So assume that for a given M and S, we assume by way of contradiction, M under S does not satisfy my phi. This is my proof that this is indeed a logical truth. So assume that for some interpretation in some structure, it is not satisfied. Then we know it must be the case by truth tables, by the truth table of arrow. It must be the case that in this structure, in this assignment, what happens to Q of Y is false. It's not satisfied. So this structure does not satisfy Q of Y. Or S hat of Q of Y is false in this structure. So, in other words, it means that S hat of, this was the notation that you used, is false. So this is that S hat of Y does not satisfy Q in M. Q in M is a relation. This is an element. This element is not in the relation. Say Q is interpreted, say my structure is the natural numbers. Q is interpreted as all the odd numbers. And S of Y, the assignment of Y, is not an odd number. Okay? Now I want to show that in that case, this part cannot be true. So in that case, I claim that, so let us check, does M satisfy, under this interpretation, for all x Q of X? And what is the answer? Will it satisfy it or not? No. Because to satisfy for all x Q of X, it has to satisfy Q of not Q of Y. It has to satisfy Q of an element, how shall I call it? Say S of X, but it's not the same S. S prime of X for, so S prime of Q of X must be right for all elements in the universe. Right. So this is satisfied. M satisfies for all under S for all x Q of X. If I just for every D in the universe, if I'll take S and replace X with D, it will satisfy Q of X, or in other words, Q of D holds, Qm of D holds for all M, for all D. Right? I satisfy for all x q of x under assignment S. If I take my assignment and replace x by any element d of the structure, this will hold. Or in other words, it means that in the interpretation of Q in the structure, every element satisfies the interpretation. But here we got a contradiction. Since we have here an element, well, where was this element? Contradiction to this. The interpretation of y did not satisfy Q. So it couldn't be the case that Q is satisfied for all elements. So let me show you, I think that more generally we'll argue more intuitively because the question, you see it here, the whole game, the whole effort was to how to show it formally. But the interesting cases is that we can feel confident about the formalism and just check what is a logical truth and what is not. So let me ask you, what is this a logical truth or not? So let psi1 be the formula. There exists y such that for every x r x y, errors for all x there exist y such that r x y. What do you think about this formula? Is it a logical truth or not? And again, I'm asking you to get out of the formalism and think about it intuitively. So what does it say? This says that if I look at the relation R, yes, what do you think?
Yeah, it's disproven because if you let R be a quality as a relation, it's pretty easy to find.
So what's your claim? Is this a logical truth or not?
No.
Oh, why not?
If you let R be a quality.
If RB is a quality, so what does this formula say? There exists a y such that every x is equal to this y.
Yes.
So this means there is only one element in my structure.
Yeah.
Okay, and there's only one element in my structure. For every x, there is a y that equals to it, because I can pick y to be the same x. Right? So let us think of it this way. What does this formula say? It says, one way of checking such formulas is to view the relation as a graph. So I have the elements of the model here, and I'll put an arrow whenever, if I have here A and B, I have in my structure R of AB. So I'll put an arrow whenever I have the structure satisfy this relation between the two elements. So this way I translate my model into a graph. If I have only a two-place relation, I can view my model as a graph. So if I view my model as a graph like this, what does the first formula say? The first formula says there exists a y such that for every x, the relation connects x to y, including y itself. Right? It says there exists a y such that everyone relates to y. And what does this formula say? This formula says for every x, it relates to someone. But if all the x's relate to the same y, it's clear that every x relates to someone. Right? In other words, this formula can say there exists some rock star that everybody loves. So this says x loves y. So So this says there exists some rock star such that every person likes this rock star. And this formula says for every person there is a rock star that he loves. So if you have a rock star that everybody loves, then everybody has someone that he loves. That's what this formula says. Now if we understand this, what will happen if I reverse the order here? So let phi 2 be if there exists an x such that if for all x there exists a y such that rxy, then there exists y such that for all x rxy. Is this a logical truth or not? So now if you think about it as the rock star, this says if everyone, or partners, everyone has a partner that they love, this formula says there is someone who is a partner of everybody. So this is not a logical truth. So this is a logical truth. This is not a logical truth. How do I show that it's not a logical truth? How should I show that something is not a logical truth? Yes? Counterexample. So I have to, what is a counterexample? A counterexample is I need to give you a structure and an assignment, but if the formula doesn't have free variables, I don't care about the assignments, in which it fails. So can you give me a structure in which the second formula fails? Yes?
Where the relation is equals over natural numbers.
Okay, that's one good solution. So here is one counterexample. Let M be, the universe is my natural number, and the relation is equals. So this says for every x there is a y such that x equals y. That's true in my structure, because for every x, who will be this y? X itself. But this formula says there exists a y so that everybody is equal to y. And that's, of course, true only if I have only one element in my universe, and here in my universe I have more than one element. So showing that something is not a logical truth boils down to constructing a counterexample. We can either take, as our world of counterexamples, structures like the natural numbers, or we can do it with graphs and edges for the binary relations. So another counterexample could be in the structure in which, say, I have my set of three elements, A, B, C, and my relation R is the edges of the graph. And now I just want to draw a graph in which for every element it has an edge to someone, but there is no element that has all edges pointing to it. So that's very simple. I can just put them like this. This is going to be my A, B, C, and here is my structure. The arrows tell me RAB holds, RAC holds, RBC holds, RAC holds. So I have the first formula. For every x, there is a y such that RXY holds, but I don't have the second formula. There is no element such that everybody is pointing to them. So two rich sources for counterexamples are either play with the natural numbers or use graphs for binary relations. So let me give you another example, and you will tell me if is it a logical formula or not. So here is another example. Let us consider the formula as follows. For every x, px arrows qx, arrows for every x p of x, arrows for every x q of x. So what do you think about this formula? Is it a logical truth or not?
Yes.
Why? How do you justify it?
If you try to make that left-hand side true and right-hand side false. Yeah, basically by contradiction. You try to make the left-hand side true.
So let's try to work. So the answer is really yes. It is a logical truth. And sure, since it's made of errors, I can just try to reason by counterexample. So if I want to show that this fails, I have to be in a situation where this gets true and this gets false. But if I want this to get false, I know that this should be true and this should be false. And this true means that for every x, p of x. But by this formula, since for every x, p of x, q of x implies q of x, I get that if for every x, p of x, then for every x, q of x, and therefore this guy doesn't fail. We can dig a little bit more into the formalism, but basically that's the reasoning here. If for every x, p of x, and already know that always p implies q, then I get that for every x, q of x, and this cannot be false. So let's move to the opposite formula. What about the formula that will take the same thing, just reverse the order? So I'll have for every x, p of x, arrows for every x, q of x, arrows for every x, px, arrows q of x. So what do you say about this formula? So this is not a logical truth, but here we have to come up with a counterexample to show it's not a logical truth. So how can anybody come up with a counterexample? We have to first feel how can it fail. What? We want to get, right, so we need to find a situation in which this is true and this is false, right? Now here I have an arrow. So how am I going to make this true? Right, if the first one is false, then I don't care anymore. If the first one is false, then this will be true. So now we want to make a situation in which the first one, it's not the case that for all x, p of x, but it is the case that for all x, it's not the case that for all x, p of x, but it's also not the case that for all x, p of x implies q of x. So can you give me a concrete example, either from the natural numbers or by just give me a collection of points and what is p and q on these points? Yes?
How you take the natural numbers and p of x states that x is equal to 1 and q of x states x is not equal to 1?
Okay, that's a good one. So I take the natural numbers. I don't even have to show you the natural numbers. Here is my universe. And this is all the elements satisfying P, and these are all the elements satisfy Q. And I have some elements here, and I have some elements there. For your case, it was the natural numbers. This was just the number 1. This was all the numbers which are not 1. What will happen in a universe like this, where P and Q are disjoint and none of them is empty? So what happens to this formula? What is the truth value for all x, p of x? False. So what is the value of this formula? true, because if I have a false at the beginning of an implication, the implication is true. What happens in this formula? Is it true that for every x, p of x implies q of x? This is false because all I need is one element here that satisfies p but doesn't satisfy q. Okay? So it seems like we can always use our common sense. It's harder than in the case of propositional calculus. But it seems like we could always use our common sense to figure out whether a formula is a logical truth or not. But remember that in propositional logic we said, although we can do it by common sense, the deciding whether a formula is satisfiable or not is NP hard. A computer will take a long time to decide it. It will take exponential time. Here it's even worse. We will show later in the class that there is no algorithm that can tell you, given a formula, if it's a logical truth or not. So it means that for every algorithm, if you have some intuitive rule in your head, how will you decide if something is a logical formula or not? I can come up with a counterexample in which your rule will be wrong. I mean, it's difficult for me to come up with something that all of you will fail on because I don't know which algorithm each of you uses. But for every specific algorithm, so it is very analogous situation in propositional calculus. So it was very intuitive to decide what's a tautology and what is not, but computationally it might take a long time. This was NP complete. It is something that takes a long time if we want to be able to handle every formula. Here it is a bit harder. We can still use common sense, but if we want an algorithm, we will prove later that no algorithm can do it. So to show you an example of something which is not completely intuitive, consider this formula. So consider the formula. The formula says that there exists an x such that p of x arrows for all x p of x. At first sight, it looks kind of a confusing formula, but what does it say? This is a very practical formula. Assume that you go to the supermarket and you want to buy, I want to buy a package of eggs. So I have my package of eggs. Here is my eggs in my package. And I look at it, and none of them is broken from the top, but maybe there is an egg that is broken from the bottom. But this tells me there exists an egg such that if this egg is not broken, then all eggs are not broken. So I don't have to pick all the eggs and check them. There is always one egg that if I check this one, then I know that all of the eggs are not broken. There is always an egg such that if this is not broken, then all eggs are not broken. And, I mean, it is kind of, you say, okay, what's the problem to check all of the 12 eggs in there? But there are tasks which, if you see movies, you know that there are tasks which are more complicated than this. Right? Assume that you got, just now we did an exchange. I gave you a suitcase full of dollars, and you gave me a suitcase full of packages of plastic with white stuff in them. And I want to check that you didn't cheat me. So in principle, I'll have to tear all the packages and check each of them, which is crazy, because then all my packages will be torn, right? But this tells me there exists one package, so that if I cut it and taste it, and it's the real stuff, then every package is the real stuff. So that's a very useful formula. But is it a logical truth or not? Yeah. Why is it a logical truth?
Because basically, so the only case wherein I can't explain it actually with words because I would probably hurt myself, so I'm not going to cut out this question now, so I'll just plug in.
Why will you? I mean,
I can't formulate a sentence that I can't, because I would mess up saying halfway through, so I'm just going to let someone else do it.
So this is a logical formula. And the idea to show it is to show, let us consider two cases. Let us consider there are two options. Either, so to show it, here is the proof. Either P holds for all members of the universe, or there is a member for which P fails. Right? This is a very clear dichotomy. I look at my universe, I fix M, we fix my universe M, and I say there are two cases. Either all my eggs are whole or there is a broken egg. These are the two cases. If it's the first case, if P holds for all elements of the universe, then this is true. And if I have an implication which ends with a true, then this is true. Always. So this is true. What happens in the second case? If there is an element for which it fails, then I will pick the existence, I will pick the broken egg. So if not all eggs are whole, if all eggs are whole, then pick any egg. If this is whole, then everything is whole, because we know that everything is not broken, right? If not, if there isn't broken egg, then sure there exists an egg such that if this is whole, then everything is whole. Because pick the broken egg. This is the one that if this egg was not broken, then none would be broken, right? So if there is a broken egg, then the existence just says, yes, it's a broken egg that you should pick here. This will be false, and therefore this will be true. But we can see already that logical truths can be confusing. So I want to, so we discussed the first semantic notion, which is phi is a logical truth. And an immediate extension of this is the second logical notion, which is sigma logically implies phi. So we have logical implication. And I said that sigma logically implies phi if, that's my definition, for every MS that make every member of sigma get true, this M and S will also satisfy phi. So it's the usual same logical implication that we had in propositional logic. The only difference is now, instead of saying for every truth assignment, I say for every structure and assignment, because this is what I need to evaluate truth. So let us consider a few examples of this. So first of all, we have the very simple lemma that we had in propositional logic, that for every sigma alpha beta, the following are equivalent. That is, sigma union alpha logically implies beta if and only if sigma logically implies alpha arrows beta. And this is since all that is involved in this claim is the arrow, all we need to worry about is the truth table of the arrow, so the proof is exactly like the proof that we had in propositional logic. So as a corollary from this, whenever we saw an implication that was a logical truth, I can say that the head implies the tail. So as a corollary, we get some examples. Based on the previous examples, we get now some examples of logical implication. So I know that there exists a y such that for every x, our xy, if this is my sigma, it logically implies that for every x there exists a y such that our xy. Because I know that this arrows this is a logical truth. Yes?
Are those not both supposed to be x's? So that there exists x for all x?
Oh, sorry. Yeah. There exists an x such that there exists y. Sorry. Yeah. You got your point. So all the examples that we saw so far, if they had an arrow in the middle, they give us some kind of a logical implication. So to get interesting examples of logical implication, I'll have to talk about that do not translate into such a formula which is a logical truth. I will have to talk about sigmas which are infinite, and I will not talk about infinite sigmas right now. So let me make one comment and then I'll move on. Notice that I'm abusing the notation of this symbol. So this symbol, have you been using it in the definition of semantics? What? Only in propositional logic. Okay, so so maybe it is in place to explain it. So I use the term M S satisfy phi stands for what I guess you said that S hat of phi equals true in M, something like this. What was the terminology, the notation that you were using? If I want to say that under the assignment S, phi holds in the structure M. So you wrote it like this? Okay, so I mean the advantage of this notation is that it's very obvious what is the assignment, what is the structure. The disadvantage is that I use the same symbol here as I use here, and these are two different meanings. But this means this formula gets value true in the structure under this assignment. This is just between two sets of formulas. Whenever all the formulas here are satisfied, then this formula is satisfied. So I'm using the same symbol for two purposes. The reason there is no potential confusion, I mean there is confusion, but there's no potential ambiguity, is that here it's used between two sets of formulas. This is a set of formulas, this is a formula. Here I use it between a structure and a formula. So if we see a structure on the left, this notation means the structure satisfies the formula. If you see a set of formulas or a formula on the left, it means this is logical implication. So this is satisfies phi, and this is logically implies. Okay, so I think that will be all for today. On Thursday, we will continue with more intuitive stuff without diving too deep into notation. Thank you.